You've got to introduce them.
Oh yeah,
You've got to see why it's here.
Oh. Hi everyone. Thanks for coming. So we've got Martin Rodgers here from BAS. Martin's part of the BAS AI Lab science team. So he works on sea ice primarily with optical and SAR in combination using AI methods to detect the extent of sea ice. And before you were at BAS, you did your PhD at Cambridge.
That's correct. Yeah.
Yes.
Yeah.
Well,
I remembered.
No.
Thanks
very much for coming, Martin.
Yeah, cheers, and thank you very much, Ben, for inviting me today and for everyone for coming along. So the backstory is Ben and I met at the Antarctic Science Conference back in September, and so yeah, that's what led to me being here today. So yeah, as Ben's already explained or mentioned, I did my PhD at the University of Cambridge, and that was in the School of Geography, where actually I was focused primarily on applying machine learning techniques, convolutional networks, which I'll talk about in a minute, to coastal science, coastal geomorphology applications. But actually today feels a little bit like the academic equivalent of going back to see your parents for the weekend, because I did my undergraduate and my master's here in Leeds, so it's really nice to be back, both within the School of Geography, and I guess my master's was where I really started to develop my remote sensing, GIS and programmatic skills. And because of the nature of the fact that primarily there weren't the same level of grants and loans to do masters back in the day, that I did have a few years gap between my undergraduate and masters. So I worked for a few years at the Environment Agency as a flood risk management and environment officer, and that was all to do with regulated business, so primarily farms and the water industry, and I also spent a couple of years as a National Flood and Coastal Risk Management Advisor at the National Farmers Union, which was primarily a sort of policy making role in terms of developing new policies at a UK and EU level. So I won't talk about any of those today, but if any of you have interest in the world of policy regulation, happy to chat about that afterwards. But yeah, so I did my master's part-time while at the NFU, and then moved on to my PhD, and now I'm at the British Antarctic Survey, where I'm working on applying very similar techniques that I developed in my PhD, but to the application of determining sea ice extent. And so why are we interested in it? This ship here is the Sir David Attenborough Boatum at Boatface, which I think most people know it as, but actually the boat is Sir David Attenborough. Boatum at Boatface was just one of the gliders, the submarine gliders that go and collect some of the measurements. But there are a number of reasons why we're interested in sea ice extent from a navigational perspective, of course, but also there are some key environmental science questions that can be answered by understanding sea ice extent. So one of the most interesting ones which came out from, or hypothesis that came out from Christie et al., Fraser Christie, at the Scott Polar Research Institute last year, was this idea that actually sea ice can act as a buttress to the ice shelves. So you have the ice sheet, which sits on the Antarctic continent mainland, and then the ice shelf is the floating part of that area connected to the ice sheet. And so there is this hypothesis now that the formation of sea ice can act to buttress and therefore reduce the rate of calving at the ice shelf front. But also sea ice plays a really important role in albedo and controlling the mixing of gases and also of heat from the ocean and the atmosphere. And so in terms of what's previously been done or what tools we have available to detect sea ice extent, by far and away from a navigation perspective, these passive microwave images are the ones that are primarily used to detect sea ice extent. So these are commonly sort of referred to as the purples, and so sea ice concentration, the darker the purple, the higher the sea ice concentration. You go through to these marginal ice zone areas that are in the yellows and the greens. And they're brilliant because they have records of sea ice extent that go all the way back to 1970, and there's also the ability to capture the imagery on a daily basis for the whole of Antarctica. But the limitation is its relatively coarse resolution from 6.5 up to 25 kilometers. So that limits the ability to use this data to make tangible decisions with regards to navigation. There's then visible multispectral imagery. So this is a MODIS image, and I'm using a false color composite of bands 3, 6, and 7 for MODIS. So band 3 is in the visible spectrum, and then 6 and 7 are shortwave infrared. And so what it means is that ice comes up appearing red in the image because it is ice reflects the visible, but it absorbs shortwave infrared. The cloud comes out looking white because it reflects everything, and the water looks black because it absorbs all of those wave bands. The benefit is that it has a finer resolution, 250 meters, compared to the passive microwave. And again, there's daily temporal coverage of the whole of the Antarctic continent, but there is the obvious limitation of cloud cover. And then finally, we have synthetic aperture radar imagery, SAR. That is finer resolution again, primarily with Sentinel-1 going down to 40-meter resolution. The limitation there is the return period of those images. So the cyan squares here show all the images that have been captured in the last 14 days. So while you can see that there are many areas that have repeat coverage, you don't nearly have the same temporal coverage as you do with these other two. But just to say that actually with SAR it's going in the right direction. So Sentinel-1C will be launched later this year. So there will then be a step increase in the coverage in these areas. And so I wanted to investigate, because there are drawbacks and there are benefits of looking at both of these image types when it comes to detecting sea ice extent. My hypothesis was whether there is a benefit in training a machine learning tool using concurrent MODIS and SAR imagery, and whether that can improve performance. And so the benefits of MODIS, or any form of visible imagery, is that it's very easily discernible where the ice and water are, but the clear disadvantage is that cloud cover prevents the ability to analyze the imagery in many locations. I just wanted to point out here as well, where you've got this kind of red glaze in the cloud, that's where the cloud is actually holding ice, and so that also gives it the impression that there is actually, you can end up with the spectral properties looking quite similar to the ice actually floating on the ocean surface. The benefit of SAR is its finer resolution, but also the fact that it is far easier to discern different properties within the ice. So, for example, it's easier to pick up, for example, that this here is actually an iceberg, and then these remaining areas here are primarily sea ice. But you have limitations with regards to ambiguous signals within the ice. So things like wind waves on the ocean can make the water look like ice, and also the development of pools of water on the surface of the sea ice can again do the flip in terms of making the backscatter properties of the ice look like water. And so this is an overview of everything which I've done within this project. So this dotted line here shows the kind of divide between neural networks, which I trained as the kind of the kind of validation case where MODIS and SAR imagery were used by themselves to train a neural network to detect sea ice extent. And then I tried two different methods by which to try and detect sea ice extent using combined concurrent SAR and MODIS imagery. So the overarching process is that there are the original SAR or MODIS imageries, and then through manual digitization, there's a team at BAS called MAGIC, which is the mapping and GIS team, and they've done a large amount of mapping of sea ice extent using SAR imagery over a number of years. So very fortunate that we already had nearly 1,700 SAR images that had been manually digitized at sea ice extent. And then there's a need with a neural network for all of the images when they go into the neural network to have the same height and width. So all of the images were patched so that they had the same width and height of 720 pixels, and that resulted with this number of patches, 80,000 or 50,000. And then one of the things that I investigated within this project was the effect of the type of patches that were included. So if you look at, it's easier to see with this MODIS image, you can see that the vast majority of pixels are either, or the patches are exclusively ice or they're exclusively water. And so what I did when I did the patching is I sort of separated it so I knew all the patches that were exclusively ice, all those that were exclusively water, and all of those that were boundary patches, so they had both surface types. And so I made 3 types of image lists. So all patches were where every single patch was included. Edge patch was where only the edge patches were included, and equal proportion patches was where there were an equal number of all ice, all water, and edge patches. So concretely, there are 3 times the amount of equal proportion patches to edge patches, if you follow. And with both of those single image type CNNs, they were there was a split of 80% to 20% training and validation data, and I used a standard UNet architecture to train the tool on. And then with the multi-image CNN, I applied 2 different methods. So the first one was a 3-band concatenation. So after doing the patching, what I did is I concatenated, so there were the first 2 bands from the MODIS and then the 3rd band from the SAR. And the reason for that is that you need the neural network, if you're using pre-trained weights, which I was, to have a 3-band input. So I had to discard one of the MODIS bands to be able to train the neural network, and then everything else was very much the same. The only thing to bear in mind with this was that I had to resize this SAR image so that it had the same spatial resolution as the MODIS before the patching took place, so that each patch covered the same spatial extent. And then the second route was this CombiNet idea. So I developed this novel neural network architecture, which is very similar to the UNet architecture, which I'll go into again in a second, but there are 2 encoder stages. So this means that rather than having this necessity to downscale the SAR in the first instance, so it's at its coarse resolution, we can benefit from the fact that we can take the SAR image in at the same resolution, at the original resolution that it comes out. And then all that happens is that there's an extra pooling layer within this encoder stage, which means that we can then connect the outputs from each layer of the convolutional network together. So I will go into that in a little bit more detail in a second. But first, I just want to kind of step through the process I got before I got to train the neural network. So as with any of these sort of machine learning tasks, you end up spending the vast majority of your time actually doing data management and generation to then put into the tool. So this is the process I use to actually generate the reference data set. So I would take the original MODIS image, and here is the original SAR image as well in B. And I would then generate just using a very basic binary mask. I would identify where open water is in blue, where the cloud is in the reddy pink, and where the ice is in yellow. And then in D, what I did is in green, I manually digitized the areas where there was cloud over water. So you can see that the kind of main areas over water, which are cloud, are now in green. And then they were then converted back into water using this manually digitized mask, so that then overall you have this binary ice water mask. So this is what I used when training. This is how I generated the reference data set when training to detect ice extent using the concurrent images. And just to say where it was not possible to see where the ice extent was using the MODIS, I would use the corresponding SAR image to be able to detect where the ice and water were. So I know that there'll be a good number of you here that have used neural networks before, but I felt just in case, I've never come across a time where absolutely everyone has. So very quickly, convolutional neural network, the key component is convolution. So you have the original input image in the top left, the convolutional kernel, which is the top right. And what you do is you multiply the value of the pixel in the convolutional kernel with the pixel in the corresponding input image. And then you sum all of those pixel values together. So in this first column here, you would have 3 lots of 10 by 1, which is 30. The middle is 3 lots of 10 by 0, which is 0. And then the right is 3 lots of 10 by -1, which is -30. So if you sum that together, you get 0. And if you continue that process going from left to right and then from top to bottom, then you end up with the output image at the bottom here. And I guess the key thing to take away is that the elevated pixel values with 30 correspond to where there was this boundary between the 10s and the 0s. So the idea really is that you use convolution neural networks to detect these salient edges, which will be in the same location irrespective of the size of the convolutional kernel that you're using. And so one of the key concepts and principles of a convolutional neural network is this idea of scale invariant features, which I just referred to then, which is the idea that if you have an input image and it goes down, and then here is perhaps the outputs going down in green and blue between at each stage of the neural network, then you'll find that the dominant ice-water boundary will be in the same location in every image, irrespective of the scale that you're looking at it. So scale invariant features are a really important part of neural networks, and it's why it goes above and beyond just using pixel-wise classification. Okay, as I said, the development which I used was to have this dual encoder stage, and so it enables the ability to, as I say, use MODIS and SAR at their original resolutions. Just to say that that then meant that because the MODIS has a resolution that is 3 times greater, so each pixel was 240 meters, whereas SAR was at 80 meters. So that meant that one SAR image had 3 times the height and width of pixels compared to one MODIS image. So in the first layer of convolution, there was then a 3x3 max pooling layer, which reduced the size of the image down to 240 by 240 from 720 by 720. And then that meant after each part of the neural network, when you do the concatenation stage, then you're concatenating images that have the same resolution. So that's the way that you get over this need to, that's the way that you can get over not needing to manually downscale yourself at the start. And another thing that has to be considered is that there are a huge number of hyperparameters that are manually set when you're training a neural network. So one of the key things that I did was to use 1B, weights and biases, which I know many of you have used, but I would highly recommend. So it's a way in which you can set the range of values that you're interested in exploring with the hyperparameters, and then using a Bayesian loss function, the weights and biases system will run the neural network many times and use different values for the hyperparameters that you choose, and from that it will try to find, I'm not going to say the optimal combination of hyperparameters, but it will find a favorable combination of hyperparameters. So the hyperparameters that I looked at was batch size, so the number of pixels that, the number of patches that the neural network is simultaneously looking at, epochs, the number of runs backwards and forwards the network takes, image data set, which is what I explained before about all images, edge images, and equal images, the learning rate, and the other key one I wanted to just mention here is the class imbalance, which isn't in this bottom image. But the class imbalance relates back to the fact that there can be a tendency, if you have one type of, I don't want to say land cover, but ocean surface cover, so if there was more water than ice in most patches, then there could be a tendency for the network to just continually predict all water, because then it's going to get penalized less because it's going to be correct more often than not. So I use class imbalance to check whether that would help. So if there's a value of 0.1, then that would mean that the network was penalized more if it incorrectly predicted ice, and a value of 10 would mean that it was penalized more if it incorrectly predicted a value of water. And so what we found by and large, or what I found by and large, is that there tended to be this over prediction of ice, which I hypothesized to be because of the fact that ice can tend to, cloud can tend to look like ice. So where you have ice cloud over water, it can, the neural network can perhaps be fooled into thinking that that is ice. So by using this class imbalance, it encouraged the neural network to try and actually predict water where it was actually water. Okay, so here are some results. So this area here is Amazon Bay, which is in Western Antarctica. So this is the original MODIS image on the left. Then the center image is the corresponding SAR image, and then on the right-hand side we have the combinate output, and I placed a binary mask here. So above 0.9 is ice, and below 0.9 in terms of the confidence is water. And just to say very, very honestly, I find with Convunet that you can just be consistent, and you can just use a consistent value of 0.9, and there isn't a need, as can sometimes be the case, to use different binary values. I've used 0.9 consistently throughout all of these results. And something that I wanted just to highlight here is the kind of difference of how the neural network seems to perform in cloud versus non-cloud conditions. So you see here the blue is an area of cloud, and the green square corresponds to an area that isn't covered by cloud. And if you zoom in on these two areas, so the blue, sorry, sorry, I don't know how that's happened, it's shuffled, but okay, so if you look at this area here, this is the blue area, and you can see in the MODIS, as I was saying before, that it's covered in cloud, and this is the corresponding SAR, and you can see that the output from Convunet has a very close relationship to, or appearance to, the original SAR image, whereas with the visible, when it is cloud-free, then actually if you focus on this iceberg here, that between the times that the image capture moved from this location, because the visible MODIS was captured first, it then drifted up to here, then you can see that actually Convunet is using the visible band. And so that's my hypothesis in terms of what the neural network is doing, and it is also what I would hope the neural network to do, because as I mentioned right at the start, it is very readily discernible to detect ice from water when you are just using the visible, whereas there are ambiguous signals that can cause an effect with the SAR. So that's my hypothesis, which I'll explain a bit more going forwards. But sorry that this has happened like this, but this is just a comparison of the results from one location using Convunet, which is the combined SAR and MODIS input, the SAR only neural network, and then the MODIS only input neural network. And so what you can see, and perhaps what you would perhaps expect, is that with the MODIS only image, there is, and let me just go back a step. This top layer is the raw output, and then this is when you apply the 0.9 binary threshold. So the yellow is where it has the greatest confidence of being ice, and the black is where it has the least confidence of being ice, i.e. it believes it's water. And so what you can see is that where there is cloud cover, in general, the MODIS-only network tends to be very uncertain as to how to classify it. And so when you apply a binary mask, you actually end up in a situation where there's quite a large amount of area that isn't correctly identified, because this area here is all ice, whereas in the MODIS-only network, it comes up as water. In the SAR-only input, I would really appreciate, actually, if anyone has dealt with SAR-only neural networks, because I've spent a long time, just being open again, trying to get a neural network to be trained using just SAR images. But I can't get it over the line, and I've not actually got to a situation where I can get these so that the output has any kind of corresponding relationship with what the original SAR image was. So if any of you have dealt with them before, like I say, I spent a long time with some bias with this, and I've not actually managed to get close. So I'd be really interested if any of you have any comments on that. But what is really great to see is with the Convunet output, then you have a situation again where, for example, in this area up here, where the boundary between the ice and water is shrouded in cloud, then the shape of the kind of border here very closely resembles what you can see here, and likewise with the location of this iceberg. This is just another comparison of the outputs from Convunet, SARnet, and MODISnet. And underneath here, these are the binary accuracy scores. So these are the percentage, effectively, of pixels that have been correctly identified. What you can see again with the CombiNet output is that the dominant boundary between ice and water is shrouded in cloud here. But actually, if you look at the kind of relief, if you like, of the ice-water boundary here in the SAR image, then the kind of main areas or peninsulas, if you like, of the ice jutting out into the water very closely resemble the boundaries here. Okay. So just that was all really quite qualitative. So in terms of the tools I used to try and quantify this, I've used precision and recall, and also binary accuracy. This is the table here of to help you understand how precision recall, they're very generic terms that are used to do with true positive is, for example, where the CombiNet correctly predicted it to be ice when it was indeed ice. And then binary accuracy, as I was explaining, is the true positives and true negatives divided by all the pixels in the image. In terms of my test set, which I tested this on, the way I generated the kind of reference image for the test set is I used corresponding finer resolution imagery or finer resolution SAR imagery, which has been captured, such as Cosmos SkyMed, which has a resolution down to single meter resolution. So that was what was used to generate the reference data set from which to validate on these test results. And what you can see is that, as was sort of alluded to on the previous visual slides, SAR imagery, it's very mixed in terms of the results that you get, and in some cases it's actually ending up getting more pixels incorrect than it is correct. ModisNet actually did better than I expected it to, and on average it got over 80% of the pixels correctly identified. But in circumstances where there is very high cloud cover, that's where you get this sort of large spread of variance in the results, because there are situations where in the 30 images that I used, the 30 image pairs I used, if there was large cloud cover in the MODIS, then it could struggle. And then with the CombiNet output, what was good to see is that you do get consistently high binary accuracy results. And a little note here, I know I haven't put any of the visualizations of the outputs from Fuse 3, but there were quite good, there was a lot of similarity in a lot of circumstances between the Fuse 3 and the CombiNet output. So the Fuse 3 is where it was just a 3-band unit architecture. My belief as to why using just a 3-band unit architecture where you concatenate the 3 bands before you put them in, my belief as to why it is the case that that doesn't work as well is because when you put that class balance loss function in to identify circumstances where you want to encourage the neural network to predict water under cloud, because there aren't 2 separate encoder stages, then the weights can't individually update, so that you have a situation where the weights just exclusively in the SAR part of the encoder can update to take into account the fact that there is cloud in that image, so therefore it's a more important pixel in that location. And the other thing I also have done is look now at versions of explainable AI. So this is trying to get under the skin of my hypothesis that in situations where the MODIS image has cloud cover, that actually it's the SAR pixels become more important because it's unable to use the MODIS pixels to determine ice and water. So what I've done for this is I've taken one MODIS image, and then I have the corresponding SAR image, but then I have commuted the SAR image. I have got other SAR images from different locations and different dates, and obviously ensured that they have the same spatial extent and so on. And then I have placed them through the pre-trained CombiNet model and looked to see how does that impact the results. And in terms of analysing how that impacts the results, I've looked at 2 things. So I've looked at it in 2 ways. So what I've done is I've collected the binary ice-water cloud mask, and I've looked at how the pixels change under the cloud compared to how the pixels change when it is not cloud covered. And so what you see is when there is no cloud cover, if you commute, i.e. if you change the SAR image, it has very little effect on the output of CombiNet, i.e. there's very little change to how confident CombiNet is that it is a ice or water pixel. So just to say this, the 0 to 0.7, it doesn't relate to whether it thinks it's ice or water, it's the absolute change in the confidence that it has that it is ice. So if it used this and this image, and in this pixel here, it said to begin with that it had a confidence of 0 that it was ice, but when it used this and this image, it said here that it had a confidence of 0.5 that it was ice, then the value would be 0.5. And so, as I was saying, when you have cloud-free areas, then actually the changes that you get if you commute the SAR image is very small, and the maximum value you get is 0.2. Whereas actually, under cloudy conditions, then you do have a situation where you get a far greater range of changes in the confidence CombiNet has that pixel is ice. There's a lot to unpack with this because obviously it doesn't definitely say that therefore that is what it is doing, but one thing you can be more confident about with this is that at least if it is cloud free, then it is using primarily the MODIS image and has less, it looks less at what the SAR image shows. But the reason there is a greater range of values here is because, of course, there'll be some circumstances where even though you're commuting the image, you still have ice in the same corresponding location in the SAR image. So because of that factor as well, the fact that actually the degree to which the ice is changing the SAR image is also changing itself, that's why you get such a great range of results. But it does at least start to unpack that idea and give a little bit more evidence that yes, it is looking more at the cloud-free pixels, and at MODIS in cloud-free and in SAR in cloudy pixels. And the final thing I just wanted to show you is to go back to what I was saying at the start, which is that currently when it comes to navigation in Antarctica, then the primary tool that's used is AMSA, which is this passive microwave data, which is shown here at 6.5 kilometer resolution. And so these purple areas correspond to the high sea ice concentration down to, as I was saying before, the greens and the yellows, which is the 10 to 20% sea ice concentration, and the blue, which is open water. So this is the original output from CombiNet at the 240 meter resolution at the bottom, and I have then subsequently downscaled that to the AMSA resolution. And just to say, in terms of the way that I've downscaled it, I've taken a kernel and passed it across, and I've summed the number of pixels that are classified as water, and that gives you an indication of sea ice concentration, i.e. the proportion of area within that area of interest that is water, that is ice. And so what you see here, I have put them on different color scales because I still don't think they're directly comparable, but what you see is that you do get a very strong likeness between what the AMSA is saying and what the neural network is saying, or what CombiNet is saying. So it provides that greater surety that it is correctly detecting ice from water. But there are some very interesting slight differences between. So for example, if you look at this original SAR image, I hope you can just make out, but there are these flows that are floating in the water just here, but there are definite gaps in the ice. It is not like a fully closed off area. Whereas if you look at the AMSA, it does give the impression that there is a complete ice bridge there. Whereas if you look at the downscaled CombiNet output, then it does show that there still actually is a way that you could navigate through that area without encountering ice. And likewise, you see it down here in terms of the fact that it's picking up that there isn't a complete ice bridge there. And I also just have on the far right here, this is a comparison to OSISAF, which until 2013 was the finest resolution passive microwave imagery that was out there. So again, it gives some real indication as to how sort of using these types of images, MODIS and SAR, can be really informative in terms of giving that greater detail of what's going on. And then this is just another visual comparison. This is smiley island here, and just to say that this area in the top left here is Case Corner. So this is land in white. Case Corner is an important location. It's a fuel stop. So the Sir David Attenborough boat goes on most years, and it will deposit fuel and other resources, food, at this location here for people who are going from the Rodgers research station and then starting to travel inland. And so understanding how sea ice conditions change in this area are really important in terms of being able to sufficiently get to this corner and also know whether it's safe to do so without getting stuck in ice. So again, going back to this visual comparison of what we get with the AMSA compared to what we get with Convunet, this is just an animation of changing sea ice conditions from the 1st of January to the 15th of February in 2018, which is the last time that they did this because then COVID hit. But you can see here how you get far more detail within the Convunet output as to how the ice is starting to disintegrate. You see the sort of development of leads or in-ice water features. With it, one will come up in a second. Yeah, you start to see some of the in-ice water features that can also help from a navigational perspective. So this is work in progress, but again, it's very reassuring to see how it can be more informative from that perspective. So just some discussion points on this bit of work, and then I was going to just spend a couple of minutes just giving a very quick and dirty overview of some of the other work going on in the BAS AI lab. Maybe one of the things that was going on in the back of your head the whole time is this idea that we have concurrent MODIS and SAR imagery, but there is a time lag between them. And with that time lag, you are obviously getting change in the sea ice conditions, which is obviously a very, very big consideration with this. So I have used sea ice drift velocity values that have been derived from Farouk et al., although there are a number of other studies that are trying to get this overarching understanding of the mean drift velocity of sea ice within the Antarctic region. And so the range goes from 0.62 centimeters to 18.75 centimeters per second, which equates, if you are to use a value of 10 centimeters per second, equates to approximately 100 to 110 meters per hour. So I use the value of 10 because if you look at these areas of green and blue that are all below 10, then that gives you a kind of indication that the vast majority of areas that we're looking for are under that value. But then also, really, a lot of areas are in this blue color, which is below 5 centimeters per second. So that equates to about 60 to 70 meters per hour. So what I have said as a consideration and discussion point for this work is that an acceptable lag time between the images is 4 to 6 hours, which equates to, if you use the 5 centimeter rule, then that equates to 300 to 350 meters within the whole time period. So that is still less than 2 Convunet output pixels, because the resolution of the Convunet output is 240 meters. So that's what I have said as a kind of limitation on this. With the fact that MODIS is collected on a daily basis, that actually then means that the impact isn't as great, because if you take actually either the image from the day before or the day after, there are a few circumstances where you won't be able to find a MODIS image that was captured within 6 hours of the SAR image. So it is a limitation, but the results do indicate that a neural network can outperform a neural network trained on SAR or MODIS imagery in isolation. And the next steps which I've started to look at, and I'd be really interested if any of you have done this again, going from the point of view of really understanding what the neural network is doing and explainable AI techniques, I have looked at layer-wise relevant propagation. And so this is an example here where a neural network is trained to identify what is in this image. So it's not a segmentation task, it's a classification task, i.e. that here is a person playing baseball as the output rather than, here's the edge or whatever. And then these areas in red highlight the locations that are most important for the neural network in determining the classification. And so I'm hoping to use that, but then apply it to the task which I have. And so I can hopefully try to identify the pixels that are most important in cloudy versus non-cloudy conditions. Okay, shall I do a run through of AI? Are we okay for that? Yeah, cool.
Yeah.
This will only take a couple more minutes. So I'll start with some work of Ben Evans, who is looking at iceberg tracking. So he has developed another pixel-wise algorithm to identify exclusively where the icebergs are within the image. And he is now developing a tracking tool which is trying to identify how these icebergs are migrating within the Basin Sea. And so to do that, what he's doing is he is using CombiNet as a binary ice water mask, with the idea being that when icebergs are clustered within ice, they will tend to move together, and they will tend to move at a slower velocity than they do if it is an iceberg in open water. So using the binary ice water mask to develop different migration models for these icebergs. And then another bit of work that has been going on in the AI lab, which a lot of you I'm sure have heard about, is IceNet. So IceNet is a sea ice forecasting tool. It again uses a UNet convolutional network, and it was passed in 40 years worth of ERA 5 data on both historic sea ice extent conditions, but also other oceanic and climatic data that is very important to determine sea ice extent, so sea ocean surface temperature, currents, so on and so forth. And so the UNet architecture is used to then forecast sea ice extent at day T+1, T+2, up to day T+180. So it does a 6-month forecast of sea ice extent. And similar to what I was explaining about this idea of sea ice, neural network interpretability and understanding what the most important parameters are, Tom did a bit of work again on permute and predict. So he would change the values for each of these parameters in turn individually and see how that then impacted upon the results. So if he changed the values for historic sea ice extent, then that had the greatest impact on the ability for the network to forecast what sea ice extent would be at T+1 and so on. And likewise, then this is a list in order of the most important parameters. So it starts to get under the skin a little bit more of what is most important for the neural network. So yeah, it becomes a little bit less black box, and you can start to understand a little bit more about what it is that's important to it, and therefore does that then resonate with our pre-existing physical knowledge of the system. And this is just a visualization of some of the outputs from it. And so the green line is the forecasted sea ice extent edge from IceNet, and the black is the observed edge. And so what has been seen is the binary accuracy is above 90% for all lead times, going all the way up to 4-month lead time for September 2012. There is a bit of a dip for September 2013 because there was a abnormally low sea ice extent in that year, which shows again this sort of issue of enter a new world of Arctic sea ice extent, and therefore how that impacts upon modelling capability. But this is work in progress, and what is now currently going on is going on further from using CNNs to use variable autoencoders or neural operators, which are more probabilistic form of machine learning to try and detect sea ice extent. And finally, this is another use case of sea ice extent that Eddie Bowler is doing. So this is the Canadian, this is the Coronation Gulf, which is in the Canadian Arctic. All of these are caribou with tide collar data, and so Eddie is developing warning metrics for shipping companies in terms of understanding when shipping operations should curtail in the Coronation Gulf. because the caribou are crossing and the impact that that could have. So this is really informative. This is coarser resolution passive microwave data, and this is the finer resolution passive microwave data, and sea ice concentration on the right there. And so you see this really neat kind of display of how the caribou wait until the sea ice concentration increases sufficiently before they then cross the Coronation Gulf. So now we're looking to combine IceNet, which is forecasting the sea ice concentration, with this information that we have about how long the caribou will wait before they cross, to then start to provide warning systems to people in the area that this is the time when it is likely that caribou will be crossing in the next week or so on, so they can try and limit shipping in those times. Yeah, that's all. Thank you very much.
Martin, we've got time for some questions. Anyone in the room has a question, then I'll go online.
Yeah, I'm just sort of wondering, how do you deal with, you mentioned about how